Okay, good afternoon, everybody. So finally managed. I'm really happy to be here in person for once after such a long time. And I hope that I'll stay in the allocated time. Okay, so my name is Giulia Manca. I'm from the University of Cagliari, and I'll talk about LACB results in peripheral and ultra-peripheral collision. Do I have to do something to get rid of No? Okay, well. It's okay, it's just the title, maybe it's not so bothering. Okay, so the outline of my talk very quickly. I'll go through the LACB detector LAC. This is the first talk of LACB today. I'll maybe go a little bit more into detail. And then I have some selected results in LEL collisions, mainly JSI photo production in peripheral LEL collision, and then coherent JSI production in LEL collision in ultra-peripheral. In between these two, I will also briefly describe the centrality measurement we have at LACB, which is new measurement, which finally will allow us to make real measurements in quark-gluon plasma. And then I finally go to conclusions and outlook. Okay, so this is the LACB detector as it was for the data that we'll present today, so for round 2. All of you are probably already familiar with this, but there is a peculiar detector since it's completely developed in the forward region. The collision point is right here. It has pretty much a geometry of a fixed target experiment. So this is the collision point. There is the tracking system, which is the vertex detector, and the tracking stations before and after the big magnet. There is a calorimeter here, calorimeter here, and the muon station after that. We also have two rich, there we are, the rich detectors here and here, which allow a very good particle identification, especially for kaon and pions. For the geometry of the detector, the rapidity coverage is between 2 and 5. So these are we're going in the very forward. And so we are, for this reason, complementary to other general purpose detectors like Atlas and CMS, and partially overlap with ALICE. Two things extra to mention. One is the around the collision point, we have a system which we call smog, which in round 2 was just with some gas in the interaction region that we could inject whenever we liked, however we liked, and that would allow us to take collisions, also to take data, also not only in collision theory, like what the LAC will give us, so proton, lead, but also proton, lead, each of these beams with the gas in the region. It was originated for measuring the luminosity in the detector and be later used for fixed target physics. So that's quite nice. I won't have any results on smog, but we'll briefly touch on that. And there is another detector which we call Herschel, which is at this distance of 110 meters from interaction point up here, which we use in this analysis mostly has to veto events, very high, very large rapidity. Okay, so the performance detector are partially here, and it can be found in this paper. As I said already, is quite precise and is born for, let's say, B physics and C and C physics mostly. And now we use this as a general purpose detector to do also other measurements. Of course, this is what it was in round 2. Now in February 2022, this detector has been very largely replaced, and there is a new one which has different, of course, highly improved performances. Okay, so with the detector I describe you, LACB is right here, is one of the 4 interaction points of the LAC. We took mainly proton-proton data, but also we had data in proton, lead, and lead proton in 2013, 2016 at 5 and 8 TeV. This is our let's say heavy ion best sample because we have a very large luminosity, about 34 inverse nanobarns in 2016, and which corresponds to about 100 million, 1 million J size. And we also took, just as in 2015, LEL collision for the very first time. This was quite exciting for us at the square root of S of 5 TeV. In the first data taking campaign, we got 10 inverse microburns, and then in 2018, we already got 20 times more. Of course, we also got collisions recorded as xenon collision, which haven't done anything yet, which is the square root of S of 5.4 TeV, and we have several fixed target mode sample with SMOG. Here is a summary of what the data set that we have. These are with SMOG, proton with each of these gases, and lead with each of these gases, and these are the collision system where we have proton, lead, proton, lead, lead, in 2015 and 2018. These are the two samples I will discuss today. So you see the size and luminosity. And for the characteristic of the detector, we won't be able to go very high centrality with this sample. So we are limited to a centrality between 60 and 100%. This will change with a new detector, but at the moment it's what I will show today. Okay, so the first measurement is a coherent GSI production in ultraperipheral lead collision. They is described in this publications, and is an even display of one of these collisions in lead. We can see the interaction point, all the tracks, and the muons here in green in the muon station. So when Dr. Zhao may already discuss at length the ultraperipheral, so I won't need to say much about it, but it's just a reminder everybody who maybe connected just now was asleep, that two nuclei, ultraperipheral collisions, when two nuclei collide with each other, and the impact parameter is larger than the sum of the two radii here, so they basically should not interact. So they don't physically touch, but they do interact anyway because they are able to exchange a photon. And the size of this interaction is increased, is largely increased by the strong electromagnetic field of the nucleus, and so we do see these events. They are dividing coherent or incoherent when the photon interacts with the nucleus as a whole or with the single nucleons in the nucleus. In this analysis, we'll discuss coherent harmonic production, where in principle is GIPSI beside West, but we'll only discuss GIPSI. And it's really interesting as measurements constraints the Gluon PDFs, as one may already said. And the ratio of these two states could, in principle, give indication of the correct vector Moson wave function in the post-scattering models like these. This is a diagram of what we discussing now, so the coherent production, so the coherent harmonic production, and this is like the difference with the two between coherent and incoherent. Okay, so what do we do with the data? So we select GIPSI in lead data, and we measure the coherent cross-section defined this way. So differential over y, and we select the number of GIPSI, and we correct for deficiency the branching ratio luminosity in the bin of rapidity that we choose. The signal selection is very easy. It's basically just two tracks and nothing else in the detector. So it's very clean signal. And for this nothing else, to the definition of this nothing else enters the Herschel that I described before, as is used to further, let's say, veto events with more than two tracks. More information about the Herschel can be found in this paper. The number of signal events and then extracted from the fit of the invariant mass of the two muons. Here is the invariant mass of the two muons, where you can see the clear signal of the GIPSI, and also the hint of the site west in the 10 inverse microbarns where these data are, this is 2015 LLS sample. The kinematic range of acceptance is the usual for the LCB, so 2 to 4.5 in rapidity, and the muons have a PT larger than 700 MeV, somewhat cuts on the selection of the dimuon. These events here in the invariant mass still have both the coherent and the incoherent components. So in order to separate the two, we may perform a fit on the transverse momentum, and you can see here the quantity that we plot in this graph is the logarithmic of the square of the transverse momentum. And for the data, which are the dots and the fits, and what we expect from both coherent in blue and incoherent is red here, dashed, are plotted. If this quantity is not very super easy to immediately, let's say, to understand, and so here up is the equivalent in MeV. And you can see when we plot this quantity, it's very easy to separate the two components. So we see clearly the coherent and the incoherent, and based on this, we can actually select just the one that we care about, which is the coherent. The components here are fitted using a template from Starlight on this quantity. So selecting now these events, we're able to perform the measurement I just described before, which is the, in fact, the differential cross-section as a function of rapidity. Here you see the LACB measurements in black, and it's compared with several theoretical predictions, which are all described here. APS 09, that's one that one might describe also before, is this one, right? In the region that we are sensitive to, so in the high rapidity region, we are basically in quite good agreement with many of the models, maybe some tension with the one of Victor here, up here, where also the uncertainties, however, larger. We also integrate over rapidity to get the total number of the cross section that you see here is about 4.5 millibars with the statistical, with the uncertainties are statistical, systematic, and luminosity one. So we can see that if we get with a better control on the uncertainty, we can certainly be able to discriminate in this region, which is the one where the models are more diversified. Of course, we have great hope on this analysis with the higher statistics we will have on the way and the 2018 LELE data, which is already been analyzed. The results are also compared with the ones of Alice. Alice is similar from the same analysis. There are the results here. The range in rapidity is similar, however, opposite in sign. So they cover between 2.5 and 4. Here are their results. And here are the two compare in the same, this should actually be the absolute rapidity. And you see the two are in agreement within 1.3 sigma. And the results of Alice also results in the mean rapidity range, which one may discuss already. Okay. So that brings me now to the next measurement, which is the self-reduction of peripheral collision. This is the first measurement where we do use our definition of centrality. And since we just have a paper out, which is here, you cannot see. Let me just spend 1 or 2 slides about the how we do this. So we're really happy to have finally this measurement. So centrality, you all know, is a quantity which basically takes into account the separation, how much the two nuclei collide, so how close they are. So it takes into account basically is a proxy, is an indication of the input parameter of the center of the two nuclei, so the distance between the center of the two nuclei. We define the centrality as a percentile of an elastic cross section, and we do this for both for LED and for LED neon. So this is the first centrality measurement in fixed target. To use this, we need a quantity which doesn't saturate, the quantity which does scale with the centrality, and we use electromagnetic calorimeter, the electromagnetic energy, energy measure in the electromagnetic calorimeter that you can see in this plot in TeV for the LED sample. And then using this quantity, we starting from this quantity, we use the Monte Carlo global models to then derive the number of quantity that we need to describe the measurements, which are the number of nucleons participating to the collision, the number of binary collision and part and call, the impact parameter B, and the number of ancestors, which is discussed here. And here you can see the distribution of these 3 particles with simulation, 3 particles, 3 quantities. Okay, so this is what we obtained then for the LED 5 TeV central mass energy. This is the electromagnetic energy in slice of centrality. So the region where we are at the moment sensitive is this region here with centrality very high. So from, let's say, 95%, we don't consider the last beam, which is very polluted by electromagnetic interaction, to 0%. But this is where the two nuclei are more central, so they more collide most. And these are the three quantities I described before. So B, the input parameter, number of collision, number of participants in slices of centrality. So here you can see the different centrality bins that we identified in the three quantities. And you see there's slightly overlap in some of the regions, and this gives an indication of the uncertainty on the centrality bins, on the quantity in centrality bins. This is the same plot for Le neon. Le neon, of course, we have less statistics. This is just one round where we there was no, we usually take smog, so lead, neon, and lead at the same time. So we collect smog data and collision data simultaneously. But for this measurement, we took a run where there was no lead, so we just lead neon interaction. You see again the electromagnetic interaction energy and per parameter, number of collisions and a number of participants. So you see now here the overlap is slightly larger, and this is why, in fact, in the final plots, the uncertainty is larger for lead neon than for lead. And here's all the numbers in all the bins of centrality that we have and all the different quantities with their uncertainty. And this can all be found in the paper that you will see, if you could see here what is written. Okay, so then using these quantities, how much are you? Okay, good. So using this definition, we can then go into describe the project production in peripheral collision. So this is basically collisions where the two nuclei touch each other, but very barely, basically. So the parameter is still less the sum of the two radii of the lead nuclei. So in this type of collisions, it's possible to identify also the hadronic component and not only the coherent component. These are the two diagrams that I'm discussing, which has been discussed already in the previous talk. Again, we're looking for Gibbs size. So this is again the invariant mass distribution of the two muons, where we can see a very clear Gibbs size peak. For this analysis, we use a sample of 2018 data. So again, 5 TeV, about 20 times more statistics. And again, in this plot, we can see both coherent and hadronic mixed. And so we use the transverse momentum distribution to separate the two. These are the value of the PT in MeV. And you can see again a fantastic resolution of the two peaks, where hadronic here at the larger PT and the coherent and very low PT. These events are supposed to show up in less than 0.3 GeV. And in fact, this is where we see them nicely. So with these events, we then go and measure. Okay, so we go and measure the yield, but before I want to tell you what about centrality of these events. So these are the plots that I didn't show before because these are specific for this analysis, where you can see the three bins that we use. And so the centrality percentile and the number of part. Okay, so with these events, we then measure the Gibbs photo production. So what we expect to be photo produced Gibbs size measurement is the one which is being, let's say, inspired by the excess observed by Alice. That at 2.76 TeV and then confirmed by a star, as it was explained in the previous talk. So this is the yield that we measure. So the yield of these events is a function of Y and PT. And so the number of events observed is corrected by efficiency, number of minimum by 7, luminosity, branching ratio, and the bin of Y and PT. The events are shown here. So the yields is as a function of rapidity of the Gibbs size. These are the bins of the data of LSCB in this particular bin of part, compare with the model by 1A, where in one case the overlap and the no overlap effects are being taken into account. You see there's not much difference in these two models, and the data are in shape consistent with the model, although on the absolute scale not with some tension, let's say. As a function of PT, same. There is a bit of there's the same shape, a bit of a normalization factor, and the two models are not very different as a function of PT integrated. And then when we do integrate over PT and Y and show the measurement as a function of M part, so these two are in just one M part bin, which is this one. And then when we do integrate and we show as a function of M part, we see some, we start to see some difference between the two models, and this is the breadth where we could actually say something about these two. We also measure the average, the average PT of the Gibbs meson, which ends up to this value. Okay, so that brings me to my summary for today. So LSCB has successfully participated in IVI and data taking in all the time that LSCB has provided us with this measurement, and we collected good statistics. For the first time, we finally have advanced results in lead collision, albeit at still high centrality. We can observe harmonic production in lead. We did it in 2015. The 2018 results are on the way, and they are using the centrality definition, the centrality measurement we have for the first time, which is very excited about. The discussion with theoretical predictions with the theoreticians are ongoing, and also with the experiments which have a similar rapidity range. And that makes it all very lively, very exciting for us. We'll have more new results soon with this data, and hopefully with run 3. And we also, speaking of which, we have some prediction what we hope to be able to do with run 3. And we should be able to go down to centrality up to about 30% at least. It's a simulation of the upgrade of what we can obtain with the upgraded detector, which is reported here. You can see that we can go up to 30% centrality in color. There's a number of clusters in the Velo and in the tracker. Okay, so with this figure, I think I can close my talk. Thank you.
Very much. Very nice overview talk. It's really impressive how PP detector develops slowly to an AI detector. It's very nice results. So, no, I mean,
thank you. Yeah,
it's really like this.
Nice to understand what you can do.
Are there questions here from the audience?
Just hope I had not missed it, but with this, let's say, data on peripheral to mid-center collision, do you have also a way to check the nuclear modification factors that, for example, were measured by Alice in the hadronic collisions in AA?
Okay, yes. So we can, in principle, because everything is in shape. And so in these 3 bins of centrality that we already had started a measurement of the nuclear modification factor RAA for the GIPSI. And now we also have the measurement of the GIPSI at 5 TeV in PP. I don't know if you saw that. So that's also quite exciting. So we actually have the real measurement to do this. However, let's say at the time that we started doing that, the tracking efficiency wasn't super sophisticated. And now with this measurement, we develop a very good tracking efficiency way to evaluate the tracking efficiency. So we could go back to that measurement, although we're getting some nice run 3 data soon. So, but I cannot promise. In principle,
sure,
the machinery is there.
It's not that you have to go back to the old data. No, just that it's a nice, let's say, cross check of
yes,
of the data.
Definitely. So if the machinery is there, with what you had before, the uncertainty was too large to say anything significant or anything meaningful. Now we could say something meaningful, probably.
Okay, are there other questions here from the audience?
May I add one? Yes, still on this collision on peripheral, when you show the centrality in a slide very fast. Just wonder whether there could be fluctuations in the definition. I guess that you defend the centrality looking at the hadronic part of the collision, right? And then you study in this centrality class the electromagnetic interaction. How the possible fluctuation in number of participants,
so
do they have influence in the observable?
Okay, so in the paper that we published on centrality, we say that our centrality measurement is very solid, up to 84%, 85% in centrality. That's where we are confident that the electromagnetic background is under control. And in the centrality measurement are a bit higher. We quote a measurement, but with the caveat that people have to make sure that the electromagnetic background is controlled. Yeah, and in the peripheral measurement I show, so in the ultra-peripheral collision, in this particular one, we have the Herschel is being calibrated on this very signal to veto that signal. So we are confident that for this measurement, where we all have a doing the centrality, the electromagnetic background is under control. And in this one, we go only. Okay, this one we go up to 95%. We eliminate the last bin for this reason, because we didn't want to mess too much with the electromagnetic, and also in this one we have control of that. So, but this is specified even in the abstract of the paper. The up to 84% we are absolutely sure, both for neon and LED, and after that we have yes, one person has to use it with a grain of salt.
Thank
So
you.
I do not see somebody here from Zoom.
I checked a moment ago, there was no.
Maybe in the meantime, I can ask my question.
Oh, sure, of course.
So, I mean, for once, really, how far you can come down probably with the lead in centrality?
With 2018 or
Yeah,
2015. Okay, so with in 2015 we have only 10 inverse microbars of data. Yes, and we took everything. So if we are able to let's say analyze the data, we have all the data. But we could have up to, let's say, 0. However, it's very unlikely that we'll manage to actually see something because the detector completely fills up at that point, and we don't. In 2018, we stopped at 60%. So in 2018, which have 20 times more data, we don't have the data, we don't have collision. We just cut that trigger line for the main sample. We still have a minimum bias sample, which with the prescale that we have with the full range. But with the existing data set, only in the 2015 we had the full centrality range. If we were able to analyze it in 2018, up to 60%.
And not after the upgrade.
After the upgrade, we will take everything. So after the upgrade, we think we can go at least up to 30%.
Okay.
Yeah. So in the LED data sample that we will take in November 2022, December 2022, if the detector is all in shape, because we are still mounting parts and there's still the sub-detector is still being assembling at the moment. But given that everything works as we expect, the simulation is being performed with the full detector, and we can at least go up to 30%. And we are working very hard on the reconstruction at the moment, using the simulation here to make sure that we get that.
Okay, so thank you very much.
Thank you.
Is there something from the chat now? So no further questions also here. So let us take it another time.